So, as we've just learned and heard how companies are using additive manufacturing in serial production, I think the next topic is just as interesting because I think additive manufacturing in tooling, jigs and fixtures brings great opportunities with it. So, therefore, I want to introduce our moderator, which will be Patrick Dunne, Vice President, Advanced Application Development at 3D Systems. Patrick, the stage is all yours.
Hi, good morning, good evening, good afternoon, everybody. My name is Patrick. I'm the VP of Advanced Application Development at 3D Systems, and I lead a team out of Berkeley, California, where we engage with designers and engineers within companies, first of all, to determine if additive manufacturing is an applicable tool. You know, you could argue that sometimes it's over applied, and part of our job is making sure that we're focused on the right things, on where there is a value proposition that can be addressed. And then once we've determined that additive is applicable, our job pivots to tool selection, so identifying what technology, what material, what process, what software, what post process is required in order to enable a workflow. So I've been with 3D Systems for nearly 22 years, and I've supported projects all over the world, including in Europe and obviously here in the United States, and across all different industries, ranging from aerospace, automotive, healthcare, silicon wafer tooling, obviously medical applications, and an area of particular interest, and something which is often kind of not elevated to the top of the list because it's not quite as cool as direct manufacturing in additive, is the concept of using additive manufacturing for tooling. And what's interesting is, and that's actually kind of ironic, is that tooling is actually one of the primary applications of additive manufacturing. In fact, if you consider companies like Invisalign and orthodontic, clear aligners and mass custom manufacturing of orthodontic tooling, about 85% of all 3D printed parts in the world on a daily basis are actually tooling workflows. So indirect sacrificial tooling workflows, whether it's investment casting or thermoforming or tooling jigs and fixtures for factory floors. So with that, today the topic of the panel today is going to be running into a deep dive on the topic with three guests, and I think I'll let these guests introduce themselves. So first of all, we have Mandy from Lego.
Hi, thanks Patrick, and thanks Link3 for this event. My name is Mandanà Moshiri, Mandy for short. I'm a material engineer. I have a PhD in additive manufacturing, and for the past 6 years, I've been working on this technology, specializing mostly on metal. In the past, I've been collaborating with a machine manufacturer, later for aviation, before landing in the tooling industry in the Lego group that I joined in 2017. And today, I'm leading the research and development for metal additive manufacturing process chain to produce mold components, covering from new design methodology to improve the printing process, and also investigating new material and how to automate the post processes. In the Lego group, in particular, in the mold factory technology department, we have been using metal additive manufacturing for production of mold parts for actually more than a decade. Because with the design freedom given by additive manufacturing, we can improve the cooling channels design, so having a better thermal management, which helps, for example, decreases cycle time, decreasing risk of warpage, and in general, having a better element quality. And most probably, if you have some Lego sets at home, it is very likely that some of the elements that you have been molded in a printed mold component. So here I just have a bunch of examples. So for example, these tall windows from the house, these are actually printed in are molded in a printed core. Lego Duplo are actually a very common application for printed mold parts because they are bigger elements, so there is much more material. And here, additive manufacturing is really making sense. And there are also some technique elements like these long plates that have been used for some cars, or the tires are actually an example where we use printed cores.
Thanks, Mandy. Yeah, and when we met earlier this week, I made a comment to Mandy that I actually learned more about mechanical engineering from playing with Lego up until I was about 17 years old than I did from any formal schooling. So I appreciate the work you're doing and the rest of your team at Lego, Mandy. Thank you. And next we have Gianluca. Gianluca, if you want to introduce yourself.
Sure. Good morning, everyone. Patrick, thank you for leading the panel, and thank you, Link3D, for hosting the event. My name is Gianluca Mattaroccia. I am an engineering fellow at the Estée Lauder companies in the Engineering Technical Center in Melville, New York. I'm basically responsible for internal design of manufacturing equipment, but I also lead the effort of the company of scouting and implementing additive processes throughout the supply chain. I am a mechanical engineer. I have a master's degree in mechanical engineering with a focus on machine design. I've been designing machines for the last 15 years. I worked in across different industries, small companies and big companies. But my experiences were primarily in the packaging machines, in the mining, industrial machines, material handling, automotive, and then lastly cosmetics. Automotive is the industry where I could touch firsthand the power of additive manufacturing on the production floor, and that's where I gained most of the knowledge and also pursue most of the interest and cultivated a passion into really developing the mindset of a mechanical engineer that puts aside the blind spot by simply looking at part-to-part cost comparison and start going deeper into the operations of manufacturing floor and understand the implications of a part that is redesigned for additive manufacturing. That led me to design hundreds of parts for most of the machines. I mean, every machine that I design, whether it being a small or a part of a large fully automated system, has at least 10% of parts that are 3D printed. And the benefits that we see throughout the manufacturing operations are, besides controlling the cost of the equipment and reducing the lead times, obviously there is a big impact on cycle times, changeover times, and these are all amazing cost savings that the company can benefit from. And I would encourage everyone, and I hope the panel today will help towards that. Every engineer out there that is looking to implement additive in their processes to look way beyond what's the part-to-part cost comparison with conventional manufacturing. So very excited about this opportunity to speak about the benefits of additive on the production floor, and I'll give you back the floor for now. Thank you.
Thank you, Gianluca. And as you can tell, we have a very experienced panel today. I mean, Gianluca already touching on the topic of economic value, of economics, not just looking at part-to-part cost, but actually looking at the signal response with respect to life cycle value of utilizing additive in order to solve problems. So looking forward to that discussion, Gianluca. And next we have Kevin Ayers. Kevin, if you'd like to introduce yourself.
Yes, I'm Kevin Ayers. I've been a mechanical engineer and design and manufacturing engineer for many years, first with the American FBI, and then site and manufacturing engineers, and just recently I just left at Danfoss Power Solutions, where I worked there in 4 years, and my primary focus during that time was in operations and tooling. So I've done many different kinds of tooling. Sometimes we need to break up tooling in different categories. There are jigs and fixtures, which I've done. Also, I've done some injection molds as well, some investment casting tools. I used a lot of reverse engineering, 3D imaging to do those things. And I've also done a lot of disposable tooling at Danfoss. where we use it for assembly aids and paint masks and many other things. I think major corporations are all adopting Industry 4.0, and additive is a big part of the digitalization process in Industry 4.0, and it just makes things a lot easier in production if you've got digitalization and additive manufacturing.
Thanks, Kevin. And I'm curious what you mentioned the American FBI. I'm curious if there's other FBIs around the world as well. You might have to.
Well, there are some companies out there that have FBI in their name.
Right. Okay. This is the real deal, right, Kevin?
Yeah.
Okay. All right. Well, we'll be careful not to ask too many questions about your work at the FBI.
All right.
Okay. So maybe just a quick question first of all, just a kind of an entry activation question. I'm just curious, maybe starting with you, Mandy. What's the first time, like the first moment you ever became aware of additive manufacturing? I'm just curious what that, if you recall that first minute that you first saw that technology.
Actually, the very first time I got to know additive manufacturing was during my master in Italy, where I was following a course on materials for aerospace, and we were also talking about how to manufacture these materials. And I've heard for the first time there about additive manufacturing, how it was working and all of that, and I just fell in love because after that I decided to do my master thesis on that, and I've just all the career decision I've ever taken after was always leading me to more and more additive manufacturing. So it was during university.
Yeah, brilliant. Yeah, once you're, it's hard to turn away from it, right? So, and Gianluca, what's your first memory of hearing about or reading about or seeing something that kind of caught your eye and was like, hang on a minute, this is new?
Yeah, so it was 2015 when reading newspapers about automotive. I was in the automotive sector at that time, that I started reading about some cool 3D metal parts that were made specifically for some machine designers. And then soon after that, I'm not sure if he's following the session today, but Greg Polston from Zometry, him and I participated to a session to introduce the new software in the industry. It was on a panel, and we started discussing about some applications for 3D printing. So we agreed to do a first part redesign, and he helped me out with some basic design guidelines was a 3D printed connectors for an automotive testing station. So that was the light for me. That really sparked the interest, and I could really see the benefits of additive in turning an idea into a living product within 24 hours. Working on a production floor get us excited that we could cut 3 weeks manufacturing times of conventional milling into 3 days, including shipping and installations and testing on the production floor. That's how I started. That was the beginning for me to say, there's so much great potential in here that it's about time to really start putting the work into this and deploy it on the floor.
Yeah, very exciting. Good timing, I say, right? Good time to be alive, right? If you're into design and manufacturing. So, and then maybe Kevin, I think you probably saw or experienced additive manufacturing before all of us. I'm curious what your kind of origin story was or is in this space.
I got out of engineering for a little bit. I was doing foreign counterintelligence work outside the U.S., and they wanted to borrow me to look at a thing called rapid prototyping machine. And I went and saw it.
1990s, Kevin?
Yeah. No, 1980s, late
1980s. Okay. All right. Now here we go.
And then and then I had reservations. I looked at that and saw it growing apart with the lights off. And I instantly fell in love with the technology and realized for the FBI, we could manufacture potentially end components in less than 24 hours. Which got the management excited, and it just took off from there. And we ended up using polymers and composites and metals before we were all done. And it was just really, really exciting. to see parts being built. Anything you can think of in your head, you can make for the first time in history.
Yeah, and I think a lot of our experiences are directly building parts for the first time. So I'm curious, what, maybe Mandy, if you can comment, has your work with Lego, has it always been tooling and indirect workflows? And if so, what's the primary tooling application that you have at Lego?
So I would say that especially for my area, the primary applications are mold components. So we print, for example, mold inserts, nozzles, cores, like parts that needs to be used in the injection molding process. So it's not the unfortunately, additive manufacturing, we are using laser powder bed fusion as a technology. And with this technology, we can't achieve the dimensional accuracy we actually require in the end. Therefore, additive manufacturing for us is a middle step. We produce a near net shape components that then we machine afterwards in order to achieve the dimensions we require and the quality, the surface quality we require. We all like smooth and shiny bricks. And we all know that with laser powder bed fusion, we can't get this type of surface after production. So what we produce is a near net shape component that then we finish afterwards in the post processes.
Very clear. Okay, understood. Because I think there's a misconception sometimes that folks are using laser fusion of metals to directly make tools. But just to reemphasize what you're saying there, it's actually using the technology to make near net shape tooling, which you then subsequently machine. I'm curious, what's the fundamental value proposition of that workflow, given it's just near net shape? We might have lost Mandy there, so maybe if we jump over to Gianluca. Gianluca, are you also utilizing metal printing to create injection molding tools, or what types of tooling are you utilizing additive for?
We utilize additive for a variety of applications. The biggest applications that we have is obviously in components for during our machine design processes. So utilize heavily thermoplastic materials and metals to achieve to enable really equipment to perform in a whole different spectrum. We do have obviously applications for injection molding tools, centrifugal moldings. We do have applications for thermovacuum forming applications. Obviously, most of the benefits that we're all familiar with in terms of fast producing complex geometries, performances, doing part consolidations, multi-materials parts in low volume production setups, and really the opportunity to take on and impact the supply chain is what we look for. We don't have one specific application. We find the case, we build a case, and then we go out and verify and really design out parts specifically with the goal in mind. Obviously, I think one of the best and most important benefits is the ability to take advantage of the complexity, which sometimes with additive can be free, right? Not all the times, but complexity allows us to, for example, consolidate multiple components into single and complex parts. This normally allows us not only to reduce the number of parts and the weight of a tool, but also the types of hardware needed to assemble things together. And when you send a part like this to the production floor, it saves an enormous amount of resources and money during its entire life. So there is no need to, for example, to carry inventories across different warehouses in the world where we keep our toolings or spare parts for our machines. So when you also you have production lines where you have to do multiple changeovers at times, and you do part consolidation through additive manufacturing, this is it's a blessing, right? So, and also when you have factories operating in a Six Sigma environment, additive can truly impact your process yield because you have fewer process steps or parts within your machines and your setups, so you're reducing the opportunity for a defect and increasing your process output. So again, there is not one single specific application, but there are so many aspects of the deployment of additive manufacturing on supply floor, on the production floor, and really starts from the machine design. It starts from the computer. It starts from the engineering mind of the person that is thinking of producing the next performing equipment or setup or jig or fixture.
Okay, and Mandy, you're back. You can hear us?
Yes. I'm sorry. I don't know what happened. I just switched the hotspot. Let's hope it holds.
No problem. Yeah, I hope you didn't say something profound for 5 minutes that you can't recall now.
I'm sorry. I said the most important things right there.
Yeah. So just curious, Mandy, if we can go back to the question.
Yeah.
There's a bit of a misconception that folks, for example, in injection molding, they attempt to use direct metal printing to create a mold insert, and then it's not accurate enough. The shutoffs aren't flat enough. The surface quality is not good enough, and they kind of end up shrugging their shoulders, wondering like, what's the point? But what you were emphasizing there is that it's actually just one component of enabling tooling, and it's enabling near net shaping of tooling with complex cooling circuits integrated, essentially. So really, additive is enabling the cooling circuits. And then you are using traditional subtractive machining methods in order to achieve the tolerances and the surface quality. So I guess I'm curious, what, how does that? Can maybe just walk us through a little bit of detail on the workflow? How do you, for example, how much extra material do you put in your near net shape tooling? How do you align the tooling? What techniques do you use? Is it EDM? Is it CNC? Is it all of the above? What's that look like if you're able to cover that a little bit?
Okay, so basically one of the benefits is for sure, as you said, the conformal cooling channels, which enables a better thermal management. So decreasing cycle time. I can, in theory, also have more cavities in the same insert, so I can also enable these. When I produce a near net shape component, I'm also reducing the requirements to have a lot of stock material, because I just print the near net shape part. So this is also another benefit, because otherwise a stock material, you need to have blocks of metals of different sizes depending on the part that you need to manufacture in the end. So this is also another benefit. Together with, if I reduce the amount of post-process, the amount of machining operation I need to do, on a near net shape part, compared with a block stock of metal, I also reduced, I reduced the amount of machining, so I reduced the lead time for that process, but I also reduced the amount of cutting tools I need to use. So there is also an economical benefits involved in starting from a near net shape. As a workflow, then of course, our goal is our end product is the brick. So we want to produce a very good, the best possible molded elements. And everything around is to enable the best possible quality for the final elements that is going to be molded. Therefore, we start with designing the mold components that we have to work with. For example, let's say a mold inserts. After the design, we usually check it. It could be that we do some simulation to make sure that the part is actually performing as it should in the injection molding process. Then we, as you said, we also add a sort of as offsets on all our parts on the near net shape part, because if you print right in the size, then you don't have much material to remove afterwards to achieve the dimensions. So we add offsets, of course, only on the areas that needs to achieve this dimensional accuracy. Not all areas of the inserts needs to achieve this very tight dimensional accuracy, so it doesn't make sense to machine this part. So we add offset, we design for manufacture. So there is the design of the mold, design for manufacturing. Then there is, of course, the printing process, the immediate process like removing powder, cutting from the build plate, the heat treatment step. And then it goes into the final machining operation that can be all of the above that you mentioned, like CNC machining and EDM. It really depends also on the type of elements that we need to mold in that surface.
multiple value propositions, starting from using less tools all the way up to higher capacity tooling, better accuracy, essentially. So quite a not a marginal value proposition there, quite a significant multi-spectrum value proposition coming from utilizing additive at Lego. Very impressive. Okay, and then Kevin, what can you give some examples of maybe some examples of in your past where you've utilized tooling where you were able to solve a problem that couldn't be solved, for example, with subtractive or formative?
Yeah, that's a good question. I got to be careful what I say here. But in Danfoss, we had situations where we had seals that were put over shafts on hydraulic pumps that were being nicked, and they would pass the test right away, but in the field they'd break down. So we were able to add some tooling, disposable tooling that could be used in so many cycles to put that over there and safely save the seal, and help quality, help cost, because we were able to reduce cost as well. The 3D printed part was actually, instead of $125 conventionally made, was $5 3D printed, very thin walled. Also, echoing what Gianluca said, I can't pronounce Gianluca, sorry.
Gianluca.
Yeah, you know, to be able to print tooling on demand has been big. You know, we have to keep inventories, but if a part breaks, we can overnight print a part, and we can make quickly ergonomic changes. But one of the biggest things is we were putting additive in 68 factories in 23 countries worldwide, and several factories worldwide were doing the same product. So when they would, once we got digital and did most of the tooling in additive, we were able to reproduce that product line in, let's say, another country virtually in a week with the parts they needed, as opposed to normal 3 to 6 months to generate the tooling and teach the operation engineers what they did there and stuff like that. And again, it's digital, so if they didn't like what was done in Iowa, they could reproduce it in Neumünster slightly different, because everything's digital and parametrically changeable. And so again, doing on-demand tooling was big.
Yes, interesting. You touched on a couple of interesting topics there. One was kind of the branch, I guess, within tooling. If you look at all the different branches and the ecosystem within additive, within tooling, you touched on the topic of disposable, whereas Mandy's more referencing permanent tooling, essentially injection molding tooling. So it's a very interesting topic, the idea of disposable kind of manufacturing aids, sacrificial aids that facilitate and enable workflow. Another topic you touched on there, Kevin, and I think it's worth exploring with the group, is the idea of distributed manufacturing versus centralized manufacturing, right? So, for example, if you have 100 manufacturing locations, you place 100 printers, and then connect that into the digital ecosystem, essentially, and you facilitate the distributed manufacturing of product, or in this case, tooling. So, Gianluca, I'm curious if that's something that you've also looked at exploring, just the flexibility and the the kind of the instantaneous connectivity of digital workflow wired into technologies that are able to convert that digital content into physical objects, and what that has enabled for your teams.
Yeah, sure. So obviously, we have done it. We continue the effort in fine-tuning it. The biggest advantages was the capabilities of shipping files across the internet rather than parts through borders, and with expensive and lengthy considerations for custom declaration forms and so on and so forth. But the biggest breakthrough, obviously, that we are seeing in continuing the implementation in distributed manufacturing across the world and putting printers on the manufacturing floor is basically nails down to two things. First, you reduce the proliferations of inventorying sitting in multiple locations in the world, we have manufacturing equipment, and many times really come down from 3 or 4 different manufacturers. So you have the same equipment located in 10 different facilities in the world, and they all need to be carrying the same inventory for spare parts. So we're actually doing, we initiated the discussions with our original manufacturing equipment to start thinking of how they can sell us 3D files in forms of spare parts rather than accumulating physical inventories in multiple locations of the world. So that reduces the square footages or square meters available for warehousing, and also, taxes space on carried inventories. But one of the other biggest advantages, obviously, is to print on demand, but also to let the personnel on the production floor to participate in the design process of the tools that they need every day. They are the ones that know exactly how a job should be performed. They can really, some of them are extremely smart. They come up with ideas or their own. Obviously, these are not $1 million, cool parts redesigned for additive manufacturing, but it really gives them the ability to design their own tools, experience the powerful of personalization, increase the ergonomics of the tools, and put that flexibility on the floor that wasn't seen with hard tools. So these are the biggest breakthrough that we see by distributing manufacturing, having printers on the production floor, cut the cost of shippings in half, just increase the flexibility and the agility, let the people from the production floor participate in the design process, make their own tools, verify, build the knowledge, show everybody else around that this is something that really makes an impact, break down the walls of skepticism, and reduce the costs for producing spare parts on demand and manufacturing aids altogether.
So you brought up something very interesting there as well, Gianluca, is that it's not the designers in the design studio that are with the creative problem-solving jigs and fixtures on the factory floor. It's the folks on the factory floor that are looking at the problem all day long, that are feeling the pain, that when you give those folks access to the printer or to the technology and you empower them to be able to engage with the technology, that they're the folks that will come up with these kind of unanticipated value propositions, essentially, right? So it's definitely
and
it's more
if I
than
may add to
distributing
this,
the technology, it's distributing the access to the creativity and the problem solving, essentially, as well, that drives it, right?
Yeah, if I may add to this quickly, another advantage in doing this is once they have developed a specific tool for that specific challenge, then we have created a digital warehouse of files. So this eliminates then the redundancies in engineering, because obviously you give a same set of challenges to 5 different engineers, they will all come up with 5 different solutions. But if somebody from the production floor, I'm just giving a name, in Hong Kong or in Shanghai, has found those solutions and designed a jig of fixtures or an aid for that specific process, now that comes up in the cloud and shows up in the manufacturing plant in Bristol, in Pennsylvania. That same operator now sees how, on the other side of the world, that specific challenge was solved. Now it doesn't go through engineering again. It doesn't ask engineering time to redesign something that was already solved. So it just simply go on the internal network, downloads the parts, prints the parts, and uses it, and actually gives feedback to the other operator across the world.
Yeah, so it's like the democratization of contribution, essentially, right? It's breaking down the this kind of hierarchy of who gets to design and who gets to problem solve, and it becomes more like kind of a Wikipedia, so to speak, right, where everybody's empowered to engage with problem solving, because now they have access to modes of manufacturing, essentially, that allow them to convert their ideas into physical realities. So super intriguing. I guess on that similar, the flip side of that, and maybe Kevin, you can comment on this, is you could argue that also opens the door on counterfeiting of tooling, right? If it's in a world where like in the music industry, what the MP3 did to the music industry or the movie industry. I'm curious if you in your line of work, if there's been conversation or dialogue about how if you're able to convert an exquisitely complex CAD file for a very critical tool that enables the production of some very confidential or intellectually protected design. I guess we see the same with Lego, right? What's your perspective on that, Kevin? Have you I guess it's a double-edged sword, right? And like any technology, some folks will make a plow, other folks will make a weapon, right? I'm just curious, what's it look like from your perspective in that field?
So I'm also an artist, and so I started talking in the art world about 12 years ago about using art for additive, and it really took off well. But we also had IP concerns with that, and solutions are being worked on. The new AMF and other file formats replacing the STL files are going to help out a lot in security. We've printed artifacts like QR codes on the bottom of the parts. And also in the art world, they're going to start doing that so that you know which serial number, basically hidden on a part. And if somebody's copying it, you can tell that it's been copied. So a lot of interesting things going on, but it needs to be done because there is a lot of piracy out in the world today on regular engineering components. People are making knockoffs of hydraulic pumps and everything. Not so much jigs and fixtures and things like that, but end components. And so we've got to protect that. And additive can really help you out in a lot of ways and helping secure parts or at least understanding there's theft going on.
Fascinating. I mean, that's the reality of any technology, right? There's always going to be pluses and minuses, right? You have to accept that and acknowledge that and embrace the positives and move forward. So Mandy, I'm curious from your perspective, you started to touch on, you actually listed quite a few of the fundamental value propositions. Is there any unanticipated value propositions that you did not anticipate? I mean, we all, when we talk about injection molding and conformal cooling, we talk about cycle times, right? But earlier you started to expand on that, where you emphasized some additional value propositions that folks might not be familiar with. Could you possibly expand upon, so beyond cycle time, can you, and beyond material savings, can you expand upon anything related to accuracy and capacity as a function of additive?
Sure. So yeah, the two ones that you mentioned are also the ones that are also very well known in literature. Like if you Google additive manufacturing and molding, these are the ones that comes out like straight away. I would say that there are also a lot of hidden benefits because there has not been a lot of research about that. For example, for the dimensional accuracy, that this is something we achieve with the machining afterwards. There are a lot of hidden costs with that, and it's also difficult sometimes to take all these costs outside and understand actually how much an additive manufactured mold components cost against a conventionally manufactured one. The common idea, the more general idea, is that the AM usually costs more. But the thing is that that's not always the case. It really depends on the final part and also how much you are actually exploiting all the additive manufacturing capabilities. For example, with by removing material where it's not necessary, like topology optimizations, weight reduction, and all of that. Because in this way you also consume less material. You have a printing time which are shorter, and by printing a near net shape component, you also decrease the amount of machining you need afterwards. So there is also a lot of cost-related aspects that are not so much that people don't talk that much because they are not of very detailed exploration and cost analysis involved with this.
Okay. Okay. Would you say that in some instances the cost of the tooling is, for example, it might be twice as expensive to use additive manufacturing to create an injection molding tool, but you get 3 times the productivity, and that's the value proposition, is your kind of your bang for your buck, if that makes
But
sense.
I would say also that there are situations in which the AM tooling is cheaper than the conventional, and it's also performing better.
Okay. So it's a win-win. Yeah. Okay, got it. Okay.
Yes.
Okay.
So there are this type of situation. Of course, it's down to the specific design, to the specific part. I don't want to say that all tooling in AM will be cheaper, but there is a gap there of analyzing the hidden cost behind, because we know that AM, because of the better design, because of the functionality that are ad hoc for the application, would perform better. But sometimes it's also cheaper to produce something with AM, but the common sense always says that AM costs more. What I want to say is not always the case. It's something that needs to be investigated for the specific case. And another thing that AM also enable is that you can also print on existing part. It's not that you always need to print the entire components. If you just need a specific cooling system, if you just need a specific features which is very difficult to machine, then but the bottom part is a standard component, you can also print on top of the standard component, and it would be a win-win in all situations, because you are the idea is not that AM should replace everything. The idea is using AM where it's making sense.
Yeah, absolutely. Yeah, I've always said that you can hammer in a nail with a screwdriver.
Yeah.
I've done it. In fact, I think I've hammered in a screw with a screwdriver at some point in my career, right? So it's a tool in the toolbox, right? And at the end of the day, you have to take a pragmatic approach to tool selection. When does it make sense? When does it not make sense? And sometimes it makes sense, Mandy, to your point, to just apply it to a small sub-component of a component. And you're constantly reaching in and out of the toolbox with additive, subtractive, formative, and you're kind of combining all of these different processes together in order to achieve your objectives. Yeah. So we'll come back to that in a minute. So Gianluca, just on the a very interesting topic that you've been kind of bringing up is how breaking down the barriers with people's understanding of additive. There's a healthy amount of skepticism in some cases. There's a full spectrum ranging from hype, and I think, Kevin, you've seen a few tsunamis of hype over the last 30 years, right? But there's a spectrum ranging from hype to, SpaceX rocket engines, embracing additive manufacturing. So I'm just very curious about how, what's your approach internally with your teams in order to kind of manage that, right? So that expectations don't run away into the impractical, but at the same time, you're not confronted by just hard negative kind of rejection of the technology. Like, how do you navigate that? What's your process for getting people's attention and for getting that traction in order to open the door and share the potential and real value proposition of additive with your teams?
Yeah, excellent question. This is probably one of the most important topics that we all in the industry have the need to address. And so challenges can be inherent to the technology. So in terms of entry cost of machines, materials, knowledge gap, educational offerings in AM, proliferations of softwares, outdated CAD modeling tools, quality validations, repeatability, and standards. But the biggest challenges that I've seen over the years in different industries, different companies, and at all levels within the companies, as obviously the internal challenges, which is the resistance to change, the status quo, associated with the fact that most of the companies, they know what additive manufacturing is. They have engineers in-house. They really love the idea of exploring, but they don't know how to do. They don't have an implementation roadmap. They don't know how to make the business case. They don't even know how to compare cost to cost. And like Mandanà was saying before, how do we go down deep into the process to scouting down all those effects on saving cost throughout life of a product. So engineers, we are all engineers. Engineers are the gatekeepers of the technologies in our companies. We are not meant to be skeptical. Yet, skepticism around additive is big. It's big because people were educated around conventional manufacturing processes, which have been around for 100 years. They feel comfortable with what they know. Additive has not been here for too long, only 30 years, even though 30 years is a long time. They've not been proven long enough. So the skepticism is mounting. It's mounting also because we went through many periods of inflated expectations and then falling short on promises. Unfortunately, this is a situation that is real. Another reason why I decided to focus most of my attentions rather than simply on redesign parts for additive, but to really change the culture within my organizations and my teams, were to start taking the different approach. Try to abandon the idea of finding the next $1 million applications in additive, chasing the idea that we have to come up with the coolest part that saves the company $1 million. There is one place where you can find $1 million and a million places where you can find $1. So chase the little opportunities, gain the knowledge, work with external service providers, understand, prove the technology, make the business case, go on the production floor, see where you can make an impact, go back to design a space, take an old design, see how you can remanufacturing through additive manufacturing. These are all exercises that smaller and larger teams and big and medium-sized organizations can do to really start proving that the technology is ready for us to improve our manufacturing processes. Then it doesn't make any sense that I see it everywhere. It doesn't make any sense to take a design that was made for a conventional manufacturing process and trying to push it to the printer. This is not the way you should do this. And if you're early on in the implementation process, remember also that your best application for AM will always live at the intersections between the low volume, high complexity, and short lead time. Train your eyes to find this around you, and you will succeed into moving along the way during the implementation process.
Yeah, low volume, high value. Yeah, and you bring a very good point that there's a lot of false negatives generated from folks that drop a design that was optimized for traditional manufacturing into a 3D printer. They get a part, it's a more expensive part. They're all standing around shrugging their shoulders, wondering what's all the excitement about it. I don't get it, right? It has to start with design across the board. Conformal cooling and injection molding is advanced design for additive, essentially. So Mandy, on the topic, on a similar topic with you, I'm assuming sounds like the selling process, the evangelizing of additive is way behind you at Lego. Is that all the way up to an executive level within your organization? Everybody understands the fundamental value proposition. Would that be correct, or is there still naysayers in your organizations that you have to that are still out there at this point? I'm curious.
There is always work to do because conventional manufacturing has been used for much longer. There is also our engineers, our mold makers, our mold designers are trained on conventional mindset, because when we talk about additive manufacturing, we are not just talking about a 3D printer, we're not just talking about a machine, we're talking about a new way of thinking, a new way of evaluating. So it requires a new mindset, and there is still this gap also in the new generations of engineers. They're not yet there, and they come to a place where still the preferred solution is conventional. So there is a lot of work to do in the change management to advocate and show what are the benefits you can see, even in an organization like ours where additive manufacturing has been out there for more than a decade. But that's because it's been much more than just a decade that we know how to use. The know-how on conventional technology is so big. And there is still this trust that we need to build more and more. So we have a lot of initiatives, because the best way to convince and to convince people why, to show them the benefits is to show, it's to teach them why they should not be scared. So we have a lot of events, like we have a lot of Go Look See in our area. We would like to start again after all the COVID situation. We try to block a bit the visitors, but this will hopefully will be over soon. So we try to get over this, and we try to share very much in detail what are the benefits, what are the pros and cons on using the technology internally, so people get to know about that more.
Yeah, stop PowerPointing and start prototyping, right? It's the key.
Actually, I would say not start prototyping, I would say start production.
Start
the
producing.
Prototyping timer.
Okay. All right, I'm going to steal that. That's very good. Excellent. Yeah, and yeah, Kevin, I'm curious if it's appropriate for us to tap into your wisdom here on this. Just like if you can give us an example of where you've kind of seen an opening, like to crack, to get a little traction, a little in with naysayers, right? An example maybe historically of where you've been confronted by somebody that was very, I guess, very dismissive of the technology, especially in the field of tooling. What was the trick, right, that you used in order to get their attention?
Yeah, first of all, there's different groups of people. You have engineers, both in R&D and operations. You've got mid-level managers. You've got corporate entities. Well, you got to be able to sell to all those. Case studies help. Examples help. Parts in your hand really help. I've had more than one manager and engineer say, "This is real metal. I thought it was half 17.4 and half tofu, in the parts." And so they say they don't believe it until they hold the parts in their hands. So we also do training and workshops where people bring your parts in, and we'll see what can be possible with that. Those combination of things, developing a relationship with people, being there to know I'm an asset to you to solve your problems. Another thing is I was beating my head against the wall on cost per part for production. And we've all touched upon that. But I think one of the hidden niches now is because of supply chain disruptions from COVID to Suez Canal to dramatic increase in sales afterwards, to losing suppliers, to trade wars, that running things in parallel, developing a conventional manufacturing process along with an additive solution in parallel from the very beginning. And when you do that, you'll get an advanced model. You'll get some limited production at first, give them your best customers to get feedback. One of my engineering managers said, "What if it's negative feedback?" I said, "All feedback is positive before you go in the tooling for production." And that makes sense. But then also when there's gaps in production, all of a sudden the cost of those parts can be paid for a lot higher. You've got the cost of space. You've got the cost of losing customers. You've got line down situations. All of a sudden you can pay 300 times the price of a part or higher, because sometimes there's penalties in these contracts if you don't produce. So and then when we go into parts and services, you have an easy decision to make when you do that. Because you've already got the cost established, the quality, the PPAP is done. So I think because of all the recent history we've had with supply chain disruption, people ought to be looking at additive in parallel. So you give your managers options. And when your managers, you solve problems for them, all of a sudden money gets let loose too. Yeah,
brilliant point. Yeah, and I like your comment there about show them apart, right? That's not steel tofu, hopefully, but because I think that's possible too. But yeah, I've always said that a picture's worth 1,000 words, and a part is worth 1,000 pictures, right? And I go into conversations all the time where I just bring a part. And this is my PowerPoint. That's it. One slide. Here you go. Put it in the middle of the table and let's talk about it. that's my PowerPoint, right? In order to, and obviously engineers and designers appreciate that efficiency, right? Versus messing around with slides. So I guess we just got a few minutes left just to wrap up. Is there maybe two really quick questions, if we can do a quick fire round, Gianluca, Kevin, and Mandy? If we were to make one recommendation on when you're looking for talent, new talent, that you would bring on board in order to help accelerate the adoption of additive, maybe just a quick 20-second elevator pitch. What do you look for? Maybe John, you go first. Or
go ahead.
Kevin, please go ahead.
Oh no, I was going to say, look for someone who's passionate about additive, that doesn't give up, that's going to think out of the box, but also that communicates well.
Good. Okay, so creative thinker, passionate, who doesn't even know what the box is, basically, is what you're recommending, right?
I agree, totally agree. Yeah, absolutely. You need the individuals who are extremely passionate that can drive this through, because you will have to fight with everyone, and figurative fight, obviously, with everybody along the way to really make your point. Get your parts done, put the parts on the floor, and go. But in a nutshell, I would love someone that comes in with an open-minded approach. Forget everything about design for manufacturing, for assembly. Start fresh. Just think product performance and see how you can get there.
Design for function. Brilliant. And then Mandy, if you've got a comment on that, what gets your attention when you're interviewing people for positions at Lego with your team?
As Kevin and Gianluca said, like the passion, the mindset, it's not really much about the background knowledge. These are things you can learn on the job. It's more like the mindset. You really need the mindset. And also, like one of my favorite movie is Back to the Future. There is the last sentence that is saying, where we are going, we don't need roads. So we are just building our own roads there. So it must be someone that is curious and courageous enough, brave enough.
Okay, so a passionate person with no experience, who doesn't know where they're going. Okay, I'll take that.
Just send our CV.
Sounds like my kind of team. Perfect. Okay, brilliant. All right, well, thank you so much, everybody. I think Janice that concludes today's panel. I think it was absolutely fantastic. Really appreciate this dialogue.
For sure, Patrick. I think we can just ask maybe 2 or 3 questions from the Q&A tab. If you're open to that. Okay. So Prabir Chowdhury asks, is anyone considering or additively manufacturing consumer products with embedded sensors, which is being done in many manufacturing tooling or industrial products?
Here, and I'm not sure if you're allowed to talk about.
So we have a bunch of new technologies that we were going to use for operational parts, where we're going to embed electronics into the tooling for different applications. One is for safety, building strain mechanisms in parts. So when they start to break, we're giving a warning. Also to embed files in the parts as well, and some logistic counting mechanisms built into the parts for operations. Okay.
That's
the iceberg. Thanks, Kevin.
Another question for Mandanà was, are today all molds and inserts at Lego 3D printed?
No, not today.
And then for all of you, how do you improve the surface roughness of the cooling channels in molds? Is there a post-processing step, or do you tweak with the laser parameters?
Or do you need to? Is another question.
Yes.
Very good point, Patrick.
Not necessarily need to.
Maybe roughly.
There is a lot of IP around this, by the way. Every company is doing something different. I will refrain from answering this. I'll have to call it off.
I'll answer, but I want Mandy to correct me. Okay, so you want increased surface roughness in your cooling channels to take away heat from mold, which reduce cycle time. But there are post-finishing tools from post-processing LC and Hammond rotofinishing. Hammond is kind of neat. You can create a fluidic focal point with a paste, which can create a 0.1 surface finish on the outside and on the inside channels of a part. So you can get processes to smooth them, but I don't know why you'd want to for injection molding anyway. Hydraulics, yes.
turbulence water helps thermal management. So
Yeah.
Probably don't want to.
Mandy's been very quiet. I suspect that she knows more than all of us.
No, but
combined on this
it's
topic.
all good points. Like from a pure material science point of view, the roughness in the cooling is actually doing what Gianluca and Kevin are both saying. So one side you have a higher turbulence, the other side having higher corrosion can also initiate higher corrosion reaction, for example. So it can, in theory, can also limit the lifetime of your tool. So it's always a balance on how much your mold components you're planning it to make it live. Is it making sense or not making sense to have an extra process? It really depends on what you're using and how long you want it to be living out there.
Brilliant. All right, Mandy, I just learned something new. You made my day. Thank you.
Appreciate it. And I guess, like, if you really want to know all these really interesting IP that's being developed, thank you, Patrick, for asking the question about what they're looking for in their talent. So you can go practice those questions. Last but not least, this is a question for you, Patrick, before we end this panel. In 2016, Gartner said we would see an estimated 75% of global manufacturing operations to be using 3D printed tools, jigs, and fixtures. What would be your estimate about the real number? And you coming from 3D systems, you probably have a better understanding of this.
I have no idea, to be completely honest with you. I'm not even going to hazard a guess. I'm not one of these people that just makes up things when I don't know the answer. So I don't know. Sorry.
Any other figures?
I don't know. I can tell you it's 100% in patient-specific clear aligners. Okay.
I would say, I'm not sure I understand there's different ways that question's been asked. So I would say, so for a company, are they using 3D printing in their operations? So 75% of those companies, I would say that's probably conservative. I think they're much higher. I think companies are using a lot of 3D printing stuff, not even knowing they're using it in operations. That's been my finding, that they're getting parts from contractors or someplace else. They don't know how it was made or anything. And since it's cheaper to make it 3D printed, it's being printed that way. They don't even know it.
Well, thank you for that wonderful closing, Kevin. I hope every one of you guys will go back to your manufacturing site and validate how true that is. And if not, maybe it's time to get started, because folks are doing this and experiencing wonderful cost savings and other additional benefits. Patrick, anything you'd like to do to close this panel before we end this for the virtual networking?
Yeah, I think, it's always a good day when you learn something, right? Certainly makes my day. So I really appreciate this conversation. I've learned a lot from Gianluca, Kevin, and Mandy, and just really appreciate the dialogue. And it's been a pleasure to engage today and have this conversation. And I'm hoping the audience as well learned something, right? I certainly did. So I appreciate that. Thank you so much. Okay.
Thank you, everyone. So today we covered so many different things on tooling, for using it for near net shape, how to use it for disposable tooling, conformal cooling. And there's so many benefits, from cost savings, reducing spare part costs for the OEM's manufacturing tools that you might normally have to warehouse, shipping costs, and how organizations are taking these solutions today, digitizing it so that they could enable on-demand manufacturing of tools and spare parts across their manufacturing sites globally, which helps on all these fronts. And what's really fascinating is seeing how they can use this technology to then empower those on the shop floor, helping them solve problems, become creative in engineering departments, like Gianluca mentioned, supporting their new solutions that they're trying to build, and then helping them look at how they can adapt it for their own operation if things are slightly different there. And what's really exciting is, some of the things that Mandanà talked about, the hidden costs of tooling, and also the potential savings there, and how you can overcome some of the naysayers. Kevin mentioned that you can host workshops, identify cost savings, and also develop parallel AM pathways as you're developing your conventional solutions. So let's say if there's a risk, Suez Canal, and hopefully not another pandemic, and other types of situations where you can have an AM parallel solution being developed, so you can reduce the risk of losing a contract, risk of losing a customer, risk of many other tangibles and intangibles. And if you're interested in finding out how all these organizations are really enabling their additive operations and want to gain knowledge on how tooling can benefit your organization or your personal learning, feel free to apply to these wonderful companies. They are looking for talented people. Feel free to review this tooling session to get all the hot tips on the 20 seconds info on what they're looking for in their candidates. So thank you so much, Patrick, for leading this wonderful panel, and everyone that's part of the delegation as well. We will now go into the virtual networking floor. Feel free to reach out to all these folks by double-clicking into the table, turning on your camera and mic, and saying hi. As well, we have a lot of additive manufacturing organizations being present today in case you have any questions you'd like to ask them on, grill them potentially, so that you could further your additive experience. Thank you very much, everybody. I appreciate you all.
Thank you, everyone.
Thanks a lot.
Have a good day.
Thank you.
Thank you.
Thank you. Bye-bye.